that week is? So how was the week?
Say normal.
Were you able to read through your slides? Or you were busy chasing money?
We did a little revision about the thermodynamics.
You have done what?
We did a little revision.
Oh, okay.
But it wasn't as usual like we used to, because it is not easy. You know, the time we use for the revision, I think now there is a power crisis. So by that time, then the light is off, and the heat and the stress, Charlie, it's not easy.
Oh, really? Is that the case?
And I think that's the new situation now. So I think we must adjust to the new situation and figure out how we will schedule ourselves.
The new normal, eh?
It's a new normal.
The new normal as well. All right, today let's talk about electricity and magnetism. Electricity and magnetism. I believe everybody have done it before. So that's
Say,
you have done something on electricity and magnetism before.
yes, please.
Oh, really?
Yeah.
That's great.
I think I did electricity and magnetism in, I think, JSS, and I think in secondary school.
It's a fundamental law that governs the universe. So when you understand it, you can do a whole lot of things. Sometimes you ask yourself, why, when you go to school, even the university, you have to study these fundamental laws? Why? Because they are the basics. When you're able to understand the basics, the rest should be very easy. You build on the basis. It's just like you have a new machine, your office. As usual, as an African, the way that is set, that's how you maintain it till the machine got spoiled. You won't try anything new because you're afraid that to get something will happen. But if you are using this wavelength, try another one and see whether I'll get the same results. If not the same result, you ask yourself why. That is a scientific way of thinking. As if Newton asks himself why the object is moving towards the earth but not going back. Why? And the why will give you an answer. And they will say you have discovered. It's not new. It has already been there. But we're able to explain to everybody's understanding. That is science. To be able to explain for everybody to understand, that becomes science. It's nothing new. It has already been there in existence. Gravity has been there Since, but only Isaac Newton that was able to explain it. This Maxwell equation about electricity and magnetism, say that, but you know Maxwell equation. Say that. I hope my people are here.
Sir, please come again.
I hope you know Maxwell equation.
Maxwell equation, no.
Or you have not come across that, eh?
No, I haven't come across that. Maxwell
Okay.
equation.
Maxwell decided to put the relationship between electricity and magnetism together as an equation. So if I may ask, what's the relationship between magnetism and electricity? What's the relationship between them?
I think it's the flow, the flow of electric, the flow of current.
Again?
Hello, sir.
Yes.
The flow of current. Yeah, between magnetic magnetic materials and electricity.
Yeah, please let me help. Let me help you.
Okay.
Okay, help me.
Okay. Good morning, sir.
Yes. Good morning.
Okay, sir. So when electricity flow through a conductor, it creates electromagnetic flux. So when electricity flow, we have a magnetic flux. So that's the relation.
Oh, really?
Yes, sir.
Oh, that's great. That's great. That's what we are here to learn, how they relate, how they interconnect, what produce what. That is the main reason why we are here. We are here to get it, make it clearer. That's the reason why we are here. Electricity and magnetism. So basically, it describes how electric charge and magnetic force are produced, how they produce forces that enable the modern device to work. Because actually, it's a force that governs about 99% of our everyday forces, electricity and magnetism. About 99% of our everyday forces. Let's talk about the MP3 that you normally play, your computers, electric motors, high energy accelerators. No, even let's talk about all the gadgets that you use, the speakers, your phone screen, the phone that you are holding, the phone screen. All this produced from this force. So if you're able to understand electricity and magnetism, a lot of things will make sense to you. That's why you are required to learn about electricity and magnetism from the beginning, so that as you move ahead, trying to fix your electric motors, trying to fix your, what do you call it, your electricity cables and all those things, high tension, high voltage and all those things, you will be able to understand why these things are happening. So we need to get the basic understanding of electricity and magnetism. So electromotive force, we say, is one of the four fundamental forces of nature. So what are the four fundamental forces of nature? They are responsible for most everyday forces. What are the four fundamental forces in nature? What are the four fundamental forces in nature? What are they?
Gravitational force.
Gravitational force, one of the force of nature. It's not Newton that produced it. He was able to explain it. These are natural. Yes, the second one.
Kinetic force.
Which one? Which one?
Kinetic.
Genetic. We are talking about genetic. And then you are entering into biology.
So I said kinetic force.
We are saying kinetic force.
Yeah. Yeah.
The force possessed by a moving body.
Yes.
All right. Any other one? I hope you have not forgotten the nuclear force that are holding the bombs. The nuclear force, the atom, the nuclear force. The nuclear forces. I hope you have not forgotten that one. The nuclear forces. And like what you're saying, kinetic energy, that we can talk about the friction, what made it move, the frictional force. So all this helps us to understand how nature behaves. So now, let's look at this. In 1819, Stark discovered that an electric current deflects a compass needle, showing a link between the electricity and magnetism. So a compass, a current deflects a compass needle, showing the link between the electricity and magnetism. So in 1819, experiment was conducted. This is just a very simple experiment. We brought a needle, compass needle, closer to electricity and realized that there was a deflection. So he asked us why that deflection. He asked us why that deflection. So we'll be able to get the separation between the electricity and magnetism. So we realize that electricity is the static shock that you receive, and the magnetism, the compass. So we realize that these two things were able to work at that time. So the current deflect the compass. So we realize that electricity to magnetism. So electricity to magnetism. The current deflects the compass. So you are moving from electricity to magnetism. So, and in 1831, that is where Faraday and Henry were performing their experiments. So they discovered that moving wire near a magnet induce electric current. That's what they realized. A moving wire near magnets or a wire induce electric currents. Wow. So from there, Maxwell unified this and other observations into a complete set of law of electromagnetism, which are fundamentals as Newton's laws of motion. These laws govern the world. The planet that we live on, they govern it. And you realize that in the sequence of experiments, a scientist, anytime you observe something, you document it. You need to document your findings, your procedures, and that explanation will make sense because each scientist, how you have discovered something, you documented it, and then another scientist will pick it up and go through the same procedure and check if I'll get the same results. That's why when you write down your procedures, you put down precautions that if you observe this, you get what I have gotten. But if you have not observed it, you get a different results. These are the precautions that you need to observe as you're trying to carry out the same experiment somebody have carried out. So through that, you're able to verify, authenticate what the colleague said, and then become the law. And you realize that these things are very beneficial to all of us and help us to understand how these things happen. So Maxwell finally unified all the colleagues have written down or discovered and put them together and call them the law of magnetism. So what are some of the experiments? Rubbing a balloon on a hair, shocking a friend after walking on a rag, show that objects can become electrically charged and exert electric forces on the small pieces of paper or on each other. Have you done this experiment in your SHS using the comb to rub your hair and used to pick a piece of paper? Have you done that before?
Yes.
Oh, really?
Some of us, we even use pen. You use the pen to rub your hair, then you used to pick the pieces of paper.
To pick the piece of paper. Eh?
Yes.
Yes. All this are telling us the relation between electricity and magnetism, the attraction, magnetism. So all these are giving you the link, how electricity linked to magnetism. They produce each other. So two types of electric charge were identified. So we have positive and negative. This was identified by Benjamin Franklin. And he realized that the electrons, they carry negative charge. And the protons carry positive charge. So what are the basic rules? Like charges repel, and opposite charges attract. These are the basic rules. And then you realize that everyday life, it happen. Yes. In everyday life, it happens. Just like a lady and lady, they are fighting. But when you say a lady and guy, massa, they'll go and eat together. These are basic rules. It applies everywhere in your life. Like poles, repel, opposite poles attract. Give me example in life situation. Are you here? I hope I'm not off.
No, you are not us.
Oh, it's only that you guys were not talking.
Sir, please, growing up when we were children, we used to play with this magnetic motors in our toy cars.
Okay.
Yes, and you realize that when you dismantle the motor and you play with the magnet in it, that one there is no identification on the magnet, but you realize that when you are playing with the magnet, when the like poles meet, you see either one magnet will be repelling, will be going back. Then the force between those two magnets, it becomes very hard for the magnet to attract. But when the unlike poles meet, that one before you realize, bah, then they are together.
That's true. That's a real life example. Any other person? You have come across something like this? You have used something that demonstrates electricity and magnetism? All right. So we are talking about two charges, the positive and the negatives. So when these two charges are equal, we can say that you have conserved them or you quantize them. Conservation or quantization of the charges. If the negative and the positives are equal, quantized them. That is the word Rutherford used. Or it's boy. So charge is conserved. Let's look at this experiment that we said. Rubbing two objects together does not create charge. It only transfers the electrons from one object to the other. So the total charge remains constant. So when you're rubbing the comb on your hair, what is happening is that you are transferring the electron from the hair, the comb, to another. And from the experiments conducted in 1909, Kant showed that all electric charges comes in integer multiples of the smallest packets. So the electron, we write the total charges as the Q is equal to n, where the n is the integer and the e, that the electron number, that 1.6 times 10 raised to the power minus 9 coulombs. These are electrons charge. So the number of the integer and the electron charge. So electric charges comes in this form. So we normally have this electric charge. These are constant value that we use in our calculation. So we know that electron has a negative charge and the proton is having positive charge. And we know that the neutrons that we know are neutral. That's what makes the atom neutral. So in that case, energy is conserved So energy is conserved. Nobody is losing, nobody is speaking, nobody is doing any other thing. Energy is conserved. Energy is conserved in that case. Energy is conserved. So now, let's talk about electric field. I want to talk about electric field. What do you know about electric field?
So electric field is a field around a current carrying conductor.
Yes. Yes. Electric field. So the region around the charge distribution where other charges fail. So for you to feel the electric field, you have to be with the area that you feel the electric field. That is what we are calling the electric field. You could be far away from the field and you will not feel the electric power. So if you get closer to where you feel the power, we call that place the electric field. The region of space around the charge distribution. Yes, the region of space around the charge distribution where other charges feel an electric force. So where you can feel the electric force, that's what we are termed as electric field. So a region that you cannot feel the electric force, then it's not the electric field. So electric field at the point is defined as the force per unit charge on a small positive test charge placed there. So we have this formula that we use. The Q is the charge and the electric field is the E. So we have the force equal to the charge multiplied by the electric field. The field is created by other charges. The test charge just feel its effects. So you are just feeling the its effect. What did the Coulomb's law says? Do you remember that law? Do you remember that law? Coulomb's law. You have forgotten, eh?
Yes, sir.
Coulomb's law gives the electric force, which is the electric field, between 2-point charges. No, it depends on the products of the charges and the force of with the square of the distance between them. You don't remember this equation? You have forgotten, eh? How do you charge an object without touching it? You charge an object without touching it. That's what we call charging by induction. Have you observed it before?
Yeah,
In
the
your
principle of transformer.
the principle of
Transformer.
oh, okay. Great. Yes. Have you come across charging object without touching it. Any other areas in life that we apply it?
So those days that we use dry cell. So sometimes when it is run down, they put it on the sun. Those days in the village, they put it on the sun from morning to evening. Then you put it back and you see that the starch a bit.
Oh, that is true. Jalebi. You grew up in the village. That is true. That is very true. This is a life experience. Sometimes we don't understand why they happen. So others are trying to explain. And when they explain, it made a lot of sense. Yes. So in everyday life, just observe and try to explain why this is happening and document it. Documentation is key as you grow up. Your activity, you're working, the place. Sometimes we only look for the usual results. You have to be conscious of some fallouts. It may be the beginning of your greatness. So no matter what you're doing, forget about the routine work. Sometimes be conscious of whatever things that may happen that may be out of the usual result that you always get. Sometimes we try to make the result looks the same. We are making a mistakes. Yes, don't do that. Don't try to do the same. No. It's not right. In science, it's not right. Don't try to forge the results. Sometimes it's communicating something to you, which you need to understand. So when you go back and look at it, you realize that you have discovered something new. That will be the beginning of your greatness. So let's be conscious everywhere that we work, anywhere that we do. Sometimes become a routine, but be observant, and something good may come out of it. Yes, the usual thing that we know, conduction, semiconductors, insulators. What do you know about conductors? What do you know about conductors?
Any material that allow electricity to flow through.
We call them conductors. All right, so who else? What do we call insulators? Another person?
So,
Yes.
insulators are materials which does not allow electricity to pass through them.
Wow. All right, another person, semiconductors.
So metal is a conductor, silver too is a conductor, which can make electric to flow.
Okay.
Okay, sir. So semiconductors, on one occasion they behave like conductors, and on another occasion they behave like insulators. So they have the property of conducting, and they have property of insulation.
All right, per this explanation of semiconductor, can somebody else put it in a different way?
Hello, sir.
Yes. Yes.
They are materials which allow partially, which allows electricity to partially flow through them.
All right, good attempt. I like the words. The key word is partial. Yes, I want just one word in the definition of semiconductors. Who else? Any other opinion? There are materials that partially allow electricity to pass through. What do you think? Semiconductors. They have both conductor and insulator property. Any other definition?
Hello, sir.
Yes.
They are materials which allows electricity to pass through them under room temperature.
Under
Room temperature.
room
And
temperature.
I don't know, mercury, I don't know if mercury can be an example.
Okay. Okay. Good attempts. Any other person? So today, it seems like we have the full class. That's looking good. Yes. Everybody should talk some. Your opinion, just express your opinion. Nobody is right and nobody is wrong. Just express yourself. What do you understand? What do you think? Semiconductors. Any other person?
Hello, sir.
Yes.
Some there are materials that lies between the insulator and then the conductor.
Great. That's a good opinion. Any other person? Yes. All right. So everything that you said, I may say everybody's right. It makes sense. But for us to upgrade on the usual definition that we know, you may say semiconductors, they are materials that are having ability to control. Hello?
I say.
So to control or to be controlled?
When I say control, it's just like we talk about air conditioning. Here we think that it's only for the cool air. If we're able to produce the heat too, are you with me?
Yes, sir. Yes, sir.
Air conditioner should be able to produce cool and hot, depending on how you set it. So to control, it could be low or high. Do you get it? The material must have that ability, that capacity to be able to control the flow. So if you are a conductor, you are taking it high. When you are semiconductor, you are bringing it low. Does it make sense?
Yes, sir.
That's science. Just say something that makes sense to people. You have done well. That's how I want us to be thinking.
Hello, sir.
Yes.
What are the examples of semiconductors?
Tell me. Yes, the question to the class. What are the examples of semiconductors?
Silicon.
Hello,
Silicon is a
sir.
semiconductor.
And which one again?
Germanium.
Okay. Kingsley, are you okay?
Yes, sir.
Yes, these are the known semiconductors we talk about?
They are in the periodic table.
Again?
Then I said they are in the periodic table.
Yeah, they are there. They are there. So these are the things that semiconductors, they are the one that is revolutionized the whole world. They are changing the world at a fast pace. And depend on the impurity that you added. What impurity are you adding? That improve the conductivity. So you are trying to control the conductivity, you add that improve the conductivity, because semiconductor itself is not that too good conductor. But when you add impurities, you doped, each one improve the conductivity differently. That is what's making the magic that now you can have a phone which is very small, can even work more than a laptop. That is the area that we are now. So we want our students to think, to be able to discover, to be able to do something new. Don't just follow the new normal and be doing the same thing as usual. Be conscious of your work, wherever that you are working, just to see whether there will be some fallouts, and ask yourself why, and go ahead to experiment it. That may be the beginning of your greatness. Never be thinking of becoming great far away from where you live. Where you live, you can be great. Just a matter of being conscious of your environment and be observant. All the great scientists, they were observant. Be observant. Ask yourself why. Charging a conductor by induction. So let's talk about this, charging a conductor by induction. So you start with the neutral conducting sphere insulated from the ground. It has equal numbers of protons and electrons. So insulated from the ground. So what it means that it's having equal number of protons and electrons. So you bring the negatively charged rubber rod near, but make sure that doesn't touch the sphere. So you are freeing the electrons in the sphere. So free electrons in the sphere are repelled to the far side, leaving the near side with an excess of positive charge, which you normally call polarization. You polarize it. Polarize it. Yes, actually, these things, we have the materials and demonstrates the practicality of it. But we are talking online. Engineer Philip.
Yes, sir.
Design a system that we could do practical online. It will be a great breakthrough.
Okay, sir. I've been designing small things. I mean, I'm not thinking about doing the big one.
That's great, senior engineer. So how to charge the sphere? By induction. So the procedures that you go through, when you're able to have your materials and put them together, you should be able to do that. You bring the charge rod close. You ground, that means you have the positive or negative. You ground it. So you remove the ground wire. When you remove the ground wire, what does it mean? The sphere now has a fewer electron than the proton, so it has a net positive charge. Remove the rod, the remaining electron distributes, leaving the sphere uniformly positively charged, without the rod having lost any charge. So you realize that the whole thing that you are learning is about the electron, proton, electron, proton, balancing them. That's why when you start your basic school, they want you to understand what is atom. All this, and when we're doing it, sometimes it doesn't make sense. But as you grow in your work, you realize the effects, how this thing you don't see them, but the effects is there for everybody to see. You don't see. Can you see electricity? It's only the effects, current, voltage. You can see, but you can see the effects, how they are producing. That's what we do. So as you move on your ladder, the workplace, academic, you will be able to appreciate what the world holds for you. These are basic knowledge that everybody needs to have. So induction in insulators, how do you do it? Insulators, what do you about inductions in insulators? In an insulator, electrons are not free to move far. So we know that they don't have, not that they don't have electrons, but most of their electrons are in the ground states. They are in the valence band. How to move to the conduction band is the only difficulty, but they have the electrons. Not that they don't have. They have, but they are not moving. The ability to move across the gap is a problem. They can. So in the insulator, electrons are not free to move far, but the charge centers inside the individual molecules can shift slightly when charged object is nearby. This polarization creates small region of excess positive charge on one side of the material, a negative charge on the other, giving a net attractive force on neutral objects. That is why charge combs attract neutral bits of paper. The molecules in the paper become polarized, and the paper is pulled toward the comb. So we are using this as an example for the explanation using the comb. So all these are things that we have done before, so I believe you can relate to what is happening here. You're able to relate. So we have done for semiconductor, insulator, so inductor, charging by induction. So you know that induction, there wouldn't be a physical contact. So the charging object keeps its own charge. And this is mostly common in electrostatic experiments, like electroscopes. So charging by conduction requires contacts between the objects. Charging by conduction, before you can conduct, you need to be in contact. The charge is transferred from one object to another. So the rod charge is reduced by the amount transferred. So charging, as we know, you put a metal cell to a fire or any hot objects. You have to conduct your spoon. You put your spoon in your cocoa. The cocoa is hot. Before you realize, the metal spoon gets hot. That's what it says. It's conducted the heat from the cocoa. The spoon conducted the heat from the cocoa. So the spoon becomes hot. So we know that Coulomb's law is the fundamental equation for the electric force between two stationary point charges. It tells you how strong the force is and in which direction it points. So what Coulomb's law says, for 2-point charge, let's say Q1 and Q2, separated by a distance, let's say R, the magnitude of the electric force, that's the Coulomb force, is what? K. The force is equal to K is, which the K is the Coulomb constant. The charges, the Q1 and Q2 over R2. And the constant value of the Coulomb's constant is given as 8.99 times 10 raised to the power 9 newtons per meter square per Coulomb square. You know this formula? Raymond,
Yes, sir.
you have seen this formula before?
Yes, please.
Have you used it in a calculation before?
Yes, please.
Oh, great. So from that equation, the force is proportional to the product of the charges and inversely proportional to the square of the distance between them. That is inverse square law. This law was established experimentally by Charles Coulomb using the torsion balance that measured the very small electric force between two charged spheres. So most of these units were not given to the people who were able to explain. So one day we are hoping to see your name somewhere that is used as a unit. Engineer,
Yes, sir.
we are waiting to see your hand products.
Okay, sir.
Yes, we have to be going towards producing a product, not only theory. Let's get a product produced. Let's work hard. So electric force is a vector. So a vector quantity should have a direction. So by the formula, if the charge is, remember, if you are not talking, you mute yourself. If the charges Q1, Q2s are greater than 0, and the signs are the same, the force is repulsive. But when the charges Q1 and Q2s are less than 0, so definitely you're going to have opposite signs, negatives. The force is attractive. Use a unit vector will be pointing from Q1 to Q2. That's what we call the unit vector. So this, what's the Newton's third law says? What Newton's third law says?
Yeah, can I try? Let me see if I can remember.
Sir,
Yes.
the law states that to every action there is an equal and opposite reaction.
For every action,
There
For
is
every
an
action force. For every action or for every action force.
all right. For every action, there are equal and opposite reactions. All right. So you can agree that the force, they should add up to 0. But if they're not adding to 0, then one will be in the opposite side. So you have seen the positive and the negatives. So if you are using the hydrogen atom, the average distance between the electrons and the proton is calculated to be around 5.3 times 10 to the power minus 11 meters. So when you're using the Coulomb's law, the electric force between them is huge compared with gravitational force. So the ratio is around approximately 10 to the power 39. Gravity is negligible at an atomic scale, as we know of. So when more than 2 charges are present, the net force on any one charge is the vector sum of the individual Coulomb force from all the others. For 4 charges, the resultant force is, so we know that F1, F2, F3, where each term is computed using the Coulomb's law and then added as a vector. I think we discussed something on vector earlier, right?
Yes, sir, yes.
Yes, how to look at vectors. So if you have been given 3 charges, you can draw this. All right. What I'll do is that I'll draw this since before I send it to you, I'll draw it for you to see. So Coulomb's laws apply to stationary objects, and it's an inverse square force, like Newton's law of gravity. So unlike gravity, the electric force can be attractive or repulsive depending on the charges, depending on the sign of the charges. For many charges, you use vector addition of all the pairwise Coulomb forces. So that's what we talk about, that superposition. You put one active and non-active superposition law. So we want to visualize the electric field line. How do you do that? We call something the Gauss law. Do you remember that law? These are the laws Maxwell put together that we call the Maxwell equation. I tell you have not before. Electric field exists in the space around the charged objects. That is true. And exerts an electric force on any other test charge placed in that region. The electric field at the point is defined as the force per unit charge on a small positive test. So electric field is a force over the charge. So mostly we use this for the equation of electric field. We have the electric field. So the force per unit charge. So it's the force over the charge. The force per unit charge. That's electric fields. The direction of the electric fields is the direction of the force on a positive test charge. If the charge is placed in the field, the force field is okay. So just a matter of making E the subject. You get the force by the charge. Do you get it? Hello? Hello?
Hello, sir.
Is somebody here?
Yes, sir. We are here, sir.
Oh, okay, that's
Oh,
fine.
okay.
Where is the lady? Is the lady here today? I can still see the only lady that we have in the class. And she won't come to class. Kingsley,
Hello, sir.
where is Papa? Is there a name Papa?
Yeah, yeah.
Yeah, yeah,
Naira.
yeah. Where is she?
Sir, for today, I don't know. I thought she'll be joining, but I don't know for now. But so unless after the class, then I'll call her to find out what the program is.
She has not been coming to class. All right. Tell her that ask of her.
Okay, sir.
So a positive charge experience force in the same direction. A negative charge feel force in the opposite direction. So that's what we know of. So electric field lines are visual tools introduced by Faraday to represent the electric field. They follow this rule. The tangent to a field line at any point gives direction of E at that point. The density of the line, the tangent to the field line at any point gives the direction of the electric field at that point. The field line starts on a positive charge and ends on a negative charge. The density of the line is proportional to the magnitude of the electric field. That is true. The density of the line is proportional to the magnetic field. So when you get closer to the line, you have stronger magnetic field. When you are far away, you have weaker field. You have weaker field. So that is what we experience. So we know that positive point charge, the field line radiates outward, but the negative point charge, the field lines radiate inward. So the dipole, that's the equal positive and negative charge line, leave the positive curve and terminate on the negative in strongest in the region where the charge is. So the dipole where the charges are high comes stronger. So for two equal opposite charges, the field is strong near each other and looks like a single charge of two of the charge at a large distance. So Gauss' law will relate to electric field over a closed surface to the net charge enclosed inside the surface. It is based on the inverse square nature of the electric field from point charges and is especially useful when the charge distribution has a high symmetry. So when you say electric flux, what does it mean? When you say electric flux, what does it mean?
So flux is normally the field around a field that a magnet generates.
Okay. Any other opinion? Electric flux.
So, sir,
Yes.
so so I'm using the magnet again. For example, those days in school, you put the magnet and we have something we call iron file. Then we'll spread it, and when you spread it on the magnet, you see how it creates the flux is generated around the magnet. So when you say so for electric for electric flux, you can say is the region or the region or the so whenever a current flow through a conductor, we have the flux around the conductor.
That is true. Yes. So basically, when you are using the field line, you want to check how many full lines that are there that are appearing. So you are measuring what you can fill, like how many. So the quantity become the flux. So you measure how many full lines on the surface. So you're trying to look at the flux, the number of flow line that you have. So normally it's proportional to the net charge inside the surface divided by the permittivity of the free space. So electric flux. So if no charge is enclosed, the net flux through the surface should be zero. That's what Coulomb's law is saying. So we normally look at the electric field as a vector field that tells you the force per unit charge at every point in space due to the same configuration of the charges. So you want to know at each point what's the electric field. So you can check that by using the force per unit charge, the force per unit charge. So you can use this to check the electric field. Can use that to check the electric field because electric field is a vector quantity. So the electric field line shows the direction and the relative strength of the electric field. Yaira, 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 are you here? So Gauss law linked the electric field over a closed surface to the net charge inside that surface and is powerful shortcut for calculating electric field when symmetry is present. So basically, Gauss law is just trying to talk about this symmetry. When there's a symmetry between, you want to check, see whether they have some equal portion somewhere. That's basically what you're trying to look at. So looking at the electric flux, you are trying to measure how much electric fields flow through a surface. So if you are trying to measure how much it flow through a surface, for a uniform electric field, that flat surface should be equal to the area. So if the surface is perpendicular to the field, then the flux will be equal to the EA, so the area. If it's perpendicular, it should be equal to the EA. Think this formula, if the surface is tilted by an angle relative to the field, the flux becomes the cos of that angle. So use the same thing, but use the cos of that angle. The cos of that angle. So the maximum flux when the field is perpendicular to the surface. So if it's perpendicular to the surface, so the field is parallel to the surface. If it's perpendicular, the theta will be 0 degree. If it's parallel, the theta will be 90 degree. So you put this into consideration, so cos 90 will give you 0, so everything will go. So long as it's perpendicular, you get your 0. So you're able to take note of this, the angles, how they are, how they behave. That's what we can look at. So in a vector language, how do you write this? The flux through a small area, that is the change in A. The vector, the magnitude, directed normal to the surface. So you are using the dot product for this to fill some the area. So you're able to have this. So you sum all up, integral of this. So this is a summation of this. So the small change, that is the dA. That's what we are doing. So the surface integral depending on both the field pattern and the shape or the orientation of the surface. So a closed surface, you divide the surface into an inside and outside out. The area vector are conventional taking outward pointing. So the net flux should be, you have integral the dA. But basically, we normally use this in the vector form. If you want to show it in the vector form, that's what we have this done. So basically what it means that if more field line leave the surface, then the quantity will be greater than 0. So if more are leaving, should be greater than 0. So if more are entering, quantity should be less than 0. So if as many enter as leave, and then it should be equal to 0, less than, equal to, greater than. These are the points that we're able to define how this varies. So Gauss' law is a fundamental statement that links the net electric flux through any closed surface to the net charge enclosed by the surface. So for a single point, that's the Q, at the center of the spherical surface of the radius, the electric field at the surface should be equal to, as we know the K to be the proportional constant, you know our Q to be the charge and the R to be the distance. I think we have defined this one already. So you are just making either subject from there. So you're able to have this as the equation. This equation is equation that we know, that we use in our calculation. So if you want to generalize it to any surface, and then we are having the in and the permittivity. The solenoid is the permittivity. This is the net charge inside the closed. So the total electric field at the surface charge inside the outside surface. So we're able to have this, the in, the A. So you're able to calculate from that area. If the closed surface encloses no net charge, the net flux is 0. as many field line enter and leaves. If the surface encloses positive net charge, the net flux is positive. If the surface encloses negative charge, the net flux is negative. More line enter than leaves. So where do we apply this Gauss law? Gauss law is always true, but it is most useful in highly symmetric charge distribution. Spherical symmetry, that's the point charge, uniform spherical shell, solid sphere. So for you to apply the Gauss law, there must be symmetry. If there's no symmetry, it's difficult to apply it. So cylindrical symmetry, any form of symmetry, could be spherical, cylindrical, or planar symmetry. Any of them, Gauss law is applied. So you must choose the surface very well. So that will be the difference between the two students, depending on how you understand it, either it's sphere, cylinder, or pillbox. To pull out the integral and the surface integral can be evaluated easily to find. So this is what you always see the Gauss law, but there are differences depending on the surface area that you are dealing with. So basically, it's always good to look at it in that dimension. So electric field, now let's talk about magnetic field. What do you know about magnetic field?
So it's a field around a magnet.
It's a field around magnet.
Yes.
Yes, it's a field around magnet. Magnetic field exists in the space around the moving charge. Current carrying wire and permanent magnets. The direction of magnetic field at any point is the direction a compass needle points there. Magnetic field lines are drawn so that they leave the north pole and enter the south pole of the magnet. So what are we talking about? We are talking about the magnetic field. What we need to take note of is that the magnetic field leave the north pole and enter the south pole. So it's just like using a battery. Current flow through a battery from where to where? When you connect battery to a circuit, what's the movement of the current?
So it go from negative to positive. But there is a there is a debate on it. They said it move from positive to negative.
I didn't get you.
Yeah, so when you connect the battery, the electron flow from negative to positive.
Okay. So mostly what we observe is that this movement is a continuum from leaving the North Pole to the South Pole, leaving the North Pole to the South Pole. It's a continual loop. It has become like a loop. It's a continuum and it has become like a loop. So we don't have any isolated magnetic pole. So there's nothing like mono pole. There's no monopoly. So this one thing about magnets that we should take note of, that the field movement. So the field is drawn from the North Pole that enter the South Pole, and it's in the continuum. So it moves like it's in the loop form. That's what's happened with a magnet. So unlike an electric field line, which start and end on charges, magnetic field lines have no beginning or end. Is it God? So that's so mostly that's what happened. You have to take note of this. That magnetic field lines have no beginning or end, but electric field lines do. Are you okay? Is that true? Is that true? Hello? Am I offline?
Hello,
Hi, sir.
sir.
Hi, sir.
Hey, you guys are there and you're not minding me.
I'm sure when we are mute, it takes a little time before the this thing comes. That's all.
It's because
I
of the net.
unmuted.
Yeah.
Oh, really?
Yes, sir.
Yo, I hear. So now, a magnetic force, which we are calling as the B, on a charged particle, the Q, moving with a velocity V in a magnetic field B, is given by the Lorentz force law. What's the Lorentz force law says? So I think this has been defined, the F, the Q, the V, and the B. That is clearly defined. So you know that the magnitude of the force. How do you find the magnitude? So you find the magnitude of the charges multiplied by the velocity, magnetic field, sine of the theta. So the theta is the angle between the V and the B. And then, so if the V is parallel or perpendicular, so it's either the theta equal to 0 or 180. So the force maximum when the V is perpendicular. So that is sine 90. Sine 90 is what? Hey, nobody's hearing me. Are you guys hearing my voice at all?
C
Yes, sir.
sine 90 is 1.
Yes, sir.
Hey, who is the one talking?
Hi, it's me. Sine 90 is 1.
Who?
Yeah, you
Yeah,
know,
you're
sir,
right.
Yaira, you joined the class 1 hour, 30 minutes later.
I'm not feeling well, please.
Yaira, you have not been joining the class.
Last week we were not having lectures. Last 2 weeks we traveled outside Accra, so there was no network.
You were chasing money.
Not really. I am a project manager, and we've started the telecom swap projects in the north. So, as part of my duties, would have to go to field and then do some other checks on site. So,
Yeah, you are looking for excuses.
no, it's not an excuse. It's my duty at work.
But you know that you have work, but you still wanted to go to school.
Because I need it. I need it.
Yeah, you
I'm,
know
I'm,
that you are occupied, but you still bought a phone.
yes, please, please. I'll call you later and so we can talk about it.
Yeah,
So that we
Ira.
don't get class. I'll call you so we can talk.
Because I don't see in class, everybody don't see in class, so that one is not. It's
I
not
told.
an
I think
obligation.
I discussed it with Kinsley the last time. I spoke to him about it. When I traveled out, I told him I was not available. So please,
So
I'll call you.
basically, the direction line across the products. So the V, the velocity, the B, the magnetic field for a positive charge. The force on a negative charge is opposite. We know something called the common right hand rule. So the right hand rule says what? The point figure along the V curl toward the B times give the direction of the force. For a positive charge, or the term along the V figures along the B, push give the force for positive charge. These are basic rules that we know, right hand rules. Right hand rules. It helps you to visualize it in that dimension. So what are some of the properties of magnetic force? So magnetic force is perpendicular to both the velocity and the magnetic field. Because the force is always perpendicular to the velocity, the magnetic field cannot change the speed of the particle, but it can change the direction of the motion. Who understand this statement?
Please, can you repeat the statement?
It's what is on the screen. And the force is perpendicular to both velocity and magnetic field. So now, because the force is always perpendicular to the velocity, the magnetic field cannot change the speed or the kinetic energy of the particle. It can only change the direction of the motion. When we say something is perpendicular, what does it mean? What's the angle?
90 degrees.
So the angle will be 90 degrees. So don't forget, with the magnetic field, we are using the sign because the sign is for the vertical, but the cos is for the horizontal. So with magnetic field, we are using the sign. So when the angle is perpendicular, the sign will be 1. That will give you maximum. But when the angle is parallel, sin 0 is what? Sin 180 is what? I don't know this thing off head.
Hello, hello, sir.
So
It's
Psalm
zero.
180 is you.
So when the force is always perpendicular to the velocity, the magnetic field cannot change the speed of the particle. You know the speed when you are rotating at that point, the speed will be changed, but the direction could be changed, which may that to come in the form of deflection. So when you buy the formula and know what is perpendicular and what is parallel, you should be able to get it. Should be able to get that explanation. So electric field and magnetic field. So magnetic field, you know the formula for electric field. The force is equal to the charge, the electric field, not the electric force. Electric force is equal to the charge multiplied by the electric field. But magnetic force is the charge, which is multiplying the velocity and the magnetic field, or the magnetic flux. The magnetic flux is multiplying the velocity and then is multiplying the charge. So by the rules, these are multiplications. So mostly electric fields always act on a charged particles, either moving or at rest. Electric field, electric force. Electric force acts on a charged particles. It's either moving or it's at rest. But magnetic force acts on only moving charged particles. It's only moving charged particles. But magnetic force acts on both moving and at rest. So if you want to talk about the direction, the magnetic force moves in the direction of the magnetic field, but for only a charged particles, positive charged particles. But when you talk about the magnetic field, it acts perpendicular to the plane. So it's always perpendicular. If it's not perpendicular, you will not feel the magnetic force. So the velocity and the magnetic fields, product of the velocity and magnetic field, So electric force can do work and can change the speeds and kinetic energy. That's electric field. Can change the speeds and the kinetic energy. When the speed is changed, and you agree that the kinetic energy will change automatically. It's just like you are using electric cars. So when the the electric force you are applying change, your car will move faster. Kinetic energy is the energy possessed by a moving body. So automatically it will move. So when you talk about magnetic force, do you know what? The magnetic force does not work. It's only change direction. Magnetic force does no work. Magnetic force does no work. Why is no work done? Why in the magnetic force no work is done? Why in the magnetic force no work is done? Why in the magnetic force no work is done? Because force is perpendicular to the velocity. Force is perpendicular to the velocity. And then what do you see cause of that? Perpendicular means supposed to be 90. So cos 90 will give you 0. So no work is done. So when you talk about work done, force. So the force lies by area. So no work is done in that sense. Electric charges but when you talk about magnetic field, moving charges and magnetic dipoles. In that case, we know that no isolated magnetic poles. They continue to move from the to the south. It's a continual movement. You have to take note of this. Work is done or not. You know, work is done when the force moves through a distance. So if the distance that it moves is 0, so no work is done. That is the science way of defining what is work. Work is done when the force moves through a distance. So if the distance is perpendicular, so if the distance is perpendicular, that will give you the cos of that angle, which is 90. Cos 90 will give you 0. So at the end, in the field of science, no work is done. No work is done in that regard. No work is done. So the compass and the natural magnets, when you use the compass and the natural magnet, it reveals that magnets have north and south poles that attract or repel, similarly to electric charges, but always in pairs. Self discovered that electric current produce a magnetic field, and Faraday and Harris shows that changing the magnetic field induce electric field. That's Faraday's law. when you are changing magnetic field, you induce electric field. So you realize that they interconnect. Electric fields induce magnetic fields. Magnetic fields induce electric fields. Can you give an example in everyday life where this happen? Are we here?
Yes, sir. Sir.
Yes. Any example where changing magnetic field induce electric field? Now, in the motors, have you worked with the motors before? You can't remember magnetic fields induce electric fields. That is how, anywhere there's a magnetic field, there's electric fields. Anywhere there's electric fields, magnetic fields. That's how it
Yes, sir.
happens.
Yes,
Yes.
sir. So, so when a movie conductor is placed in the magnetic field, we have it generates EMF, or what is electromotive force.
Yes. Yes. That's what happens. Those are the understanding that we need to have or need. So that's Faraday's law. So Maxwell equation unified electricity and magnetism into electromagnetism, showing that changing electric fields generates magnetic fields, vice versa. So magnetic fields surround moving charges. Any moving charges surrounded by magnetic fields and act on the moving charges, which we know that is perpendicular force given by before that we know, and cannot change kinetic energy. The direction can never be changed by a key contrast with the electric fields. But for electric fields, act in both sides, but in this regard, never change. This is what we need to know about electric field and magnetic field. One produce the other. One produce the other. So long as you put it there, magnetic fields produce electric fields. They work changeably. They are not in isolation. They work. So when you use the comb to rub your hair, static force and attraction will give you magnetic force. So these are the two things that work together. Static force, rubbing the comb in your hair and using it to pick. So you have the electric field that you have generated. So that's able to help to pick the paper, which is magnetic attraction. So basically, these two things work together in our motors, in our engines, and all the gadget that we prepare. All these two principle works perfectly. So it's good for you to understand how these things work, and we need to read around this area. So next week We'll take our last topic. We'll take our last topic next week. And the following week, we'll write our midsem and wait for the exam. So next week, we are meeting to discuss our last topic. And then from there, the face-to-face, we'll write our midsem. So from there, and we wait for the exam to come. Any question? Our time is up. Thank you for coming.
Yes, sir.
Yaira, yes. Kisley,
Sir, please, this Kingsley. Sir,
again?
please, I wanted to find out if the midterm is G's or the midterm is it of G's?
Is it of G?
Yes, sir.
Yes, it will be objectives. Yeah, the mixer will be objectives.
Oh, okay, sir. Okay, sir. All right,
Yeah,
thank you, sir.
okay. Is Yaira here or she's gone?
Hello,
Yaira?
sir.
Yes, Raymond.
Please, what will be the next topic next week?
The next topic next week should be light and optics.
Okay, thank you.
Light.
So is that all for this topic?
That's all for the semester.
Ah,
That is all for the semester.
okay.
Sir, please, you said that the topic for next week is what?
Light and optics.
Okay, sir. Okay, sir. Please,
Yes.
can you have the slides in advance before the class and today's slides?
All right. I'll do that.
All right, sir. Thank you, sir.
Thank you. Enjoy the rest of the week. Yaira came and left, right? Yaira will never stay for a minute because she thinks that she's too busy than everybody. All right. Bye-bye.
Bye, sir.
Bye.